Consider the problem with 9 charges, each -2 microcoulombs, equally spaced around a circle of radius 10 centimeters. What's the field, the electric field of course, at the middle of the circle? So you've got to pause and write a few things down. You should do your best to solve this problem, or at least sketch the solution in sufficient detail that you're sure you would be able to get a solution, or you're sure where your questions are. Then come back and see what I do. First thing I'll do is sketch a circle, sketch 9 charges equally spaced, represent at least 9 charges equally spaced around the circle. Those charges will be at 40-degree intervals. 360 divided by 9 is 40. Now, I observe a couple of things. One is none of these charges are diametrically opposite the other. If I had 10 charges around the circle, then each charge would have another one symmetric through the center with itself, and those 2 charges would produce opposite contributions to the field at the origin, so the total field would be 0. In this case, that might not work out. There are 9 charges. They can't be paired up diametrically opposite. Maybe there's a way you can use some aspect of symmetry to come up with a simple solution, as we would if we had an even number of charges. But let's proceed for now as though we can't do that, and then once we get a solution, let's see if there's a way to shortcut it. The next thing I would do is sketch the field vectors, and I did that. Seems like after I got to this point, the field vectors started getting bigger, so this vector is clearly bigger than this one. It might be that they grew all the way around, but they're supposed to depict vectors of equal magnitudes. Okay, hopefully you've calculated these vectors. Now I'm expressing the vectors around here as I calculated them very approximately. Your calculations should come out fairly close. Let's make sure all these make sense. Now these are in multiples of 10 to the 6th newtons per coulomb. I didn't have room to write the 10 to the 6th or the unit, but we understand that the units of all these vectors are in newtons per coulomb. And I haven't written the vectors down here yet, and you might understand why. So it looks like -1.8, yeah, -1.4, yeah, the x is greater than the y at 40 degrees. At 45, they're equal. And here, the y is going to be greater in magnitude than the x, and everything is negative around here because you're pointing toward the center. The x components go toward the origin in the negative direction. The y components are all downward. Over here, the x components will all be positive. A smaller x component here, yeah, that checks out. And a larger x component here, yeah, that checks out. The y component's negative in both cases. Now, there is a degree of symmetry here. Down below the axis, everything that we've got down here is symmetric with what we have up here. Say, as we move this way, and then as we move this way, so that this vector here is going to be, again, -1.4, but it's going to be +1.2. And we shouldn't be surprised. We have a circle here. There's regular spacing on the circle. It shouldn't be surprising that we get some sort of symmetry. And you see that when we add this vector and this vector, we don't need to bother to add the y components. They're just going to add up to 0. Down here, we're going to have the -0.3, -1.8, and it's going to be +1.8 now. Okay, and over here, we have similar symmetry. We're going to have 0.9, 1.6. We're going to have 1.7, 0.6. So right there, in multiples of 10 to the 6 newtons per coulomb, we have our fields. Now we're going to go ahead and add these up. And as I said, you can see by the symmetry that these y components are going to add up to 0, aren't they? Okay. Now, are the x components all going to add up to 0? The y components are going to cancel out here and here, here and here, here and here, here and here. What's going to happen with the x components? Okay, well, we find that the y components add to 0 in pairs, so the total y component is 0. And the total of the x components is going to be negative 5.2. That's what we get. Negative 0.3, negative 1.4 is negative 1.7. We have that again here. It's negative 3.4. And negative 1.8 gives us negative 5.2. 0.9 and 1.7 is 0.26 or 2.6, and double that is 5.2. So we do get 0, but the question now is that really 0? Or is that an anomaly of my rounding? Okay, is it something that's close to 0 but not exactly 0, or is it exactly 0? Now we kind of suspect, since the y components all added to 0, that maybe the x components really do add to 0. But can we substantiate that in any way? Okay, what we've determined is that the y components of all these vectors add up to 0. Well, the y components are the components perpendicular to this particular vector. So the components along this particular direction do add up to 0. Now, if I rotated this disk, not keeping the x and y coordinate system where it is, but if I rotated the disk 40 degrees in either direction, then this point would rotate either to this point or this point. Let's say we rotate it in this direction. This point rotates to this point. It's still going to be the case that the components perpendicular to this line, now rotated here and having this direction, add up to 0. Or that if we rotate it down to here, the components perpendicular to this vector would have to add up to 0. In fact, we could establish that the components parallel to any tangent line to the circle have to add up to 0. Now, does that help establish that the sum of the x components has to be 0? Okay, hopefully you've thought about that a little bit. I'm going to invoke a little bit of linear algebra just as one way of proving that this is so, and there are many others. Okay, I'm going to take a vector here. Okay, so clearly, first place, the components perpendicular to any of these vectors, tangent to the circle at any of these points, certainly have to add up to 0. Okay, so the components perpendicular to this vector are along the line of this vector. And let's just take this vector here because we can label it. Okay, the components along this line, which means the components parallel to this vector have to add up to 0. Now, what we have is components parallel to this vector have to add up to 0. The components parallel to this vector have to add up to 0. This vector is linearly independent of this vector in a two-dimensional space, so these two vectors span the space. And it's a straightforward argument from that the components perpendicular to any vector in the space would have to be 0. Okay, so that's an argument. You can still flesh out that argument a little bit. I'm not going to go into the detail. A little more elegant argument. I was going to do another argument, but let's just complete this one. The components of the net field are 0 in both directions. Okay, well, we have the two vectors here that span R2. The components of the field have to be 0 in the direction of this vector, have to be 0 in the direction of this vector. So it turns out, since the two vectors span the space, that the components of the net field is 0 in all directions, in any direction. Because any vector can be written as a linear combination of these two vectors, then the components in the direction of that any vector would be the sum of the components in the direction of these two vectors. Since components 0 for both, then it's 0 for the new vector. Okay, so that's just one example of a symmetry argument, a rotational symmetry, the kind of symmetry you expect with a circle. There are all kinds of other arguments. You could do the relationships of the sines and cosines of these various angles. many other ways to approach the argument, and you want to be aware of those possibilities. The brute force argument is to calculate the components of these vectors, but since the components can't be calculated exactly, you're never going to be completely, absolutely 100% sure that they're zero unless you resort to a more sophisticated argument.